In the end, it's efficiency in electrical efficiency and packaging in the car, the amount of space you get back. So basically, we compared a number of different concepts. We looked at onboard motors, we looked at close-to-wheel motors, we looked at multiple onboard motors, multiple different configurations. And we looked at what's the final impact on our main scoring parameter, which for this car is the amount of miles you can drive each year on the sun. And then if you look at in-wheel motors, it's having a direct drive, so direct from electrical to just one rotational part. There's no mechanical, the only mechanical losses you have are in the bearing of between the rotor and the stator. And there's no gears anymore in between. So you get rid of all those losses that you have there. And especially the losses you also have with the constant velocity joints that have to be moving, that you get out of it. So even if you had direct drive, but then close to wheel and you still would have the constant velocity joints, then you still have quite some losses there. So you get rid of a lot of losses on one side. On the other side, you also gain, or lose, actually, you lose mass because you get all the other components out. So it's a lighter solution in the end. And you get a lot of packaging space back, which we were able to use for two things. One, to optimize the aerodynamics on the underside of the car. So that gave us actually quite some advantage in aerodynamics again. Because there's no drive shafts and that sort of things and no final drive in the bottom, you can optimize the covers on the inside of the wheel much better. And because there was no components in the middle between the wheels in the front side, we were able to move most of the thermal management further forward so that we could create extra space in the cabin in the interior. So it's a radial flux permanent magnet synchronous machine. The reasoning actually is the main choice for us. So it had to be a permanent magnet machine because of the torque density. The biggest issue you can run into is the amount of unsprung weight you have in each wheel. So you need an as high torque density as you can, and because there's no gear ratio, you need quite a bit of torque on the direct drive motors. So that drives the volume of your motor up, and so to get to a reasonable torque density there, we had to use a permanent magnet motor. Then if you go to permanent magnet and you look at the shape of a wheel, you might immediately have the association with an axial flux machine. Because those usually look more like pancakes, right? So we did quite an extensive study to find out if in the end, in terms of efficiency and torque density, it would be more efficient to make an axial flux machine. Actually, our first prototype were axial flux machines or a radial flux machine. And in the end, we are very close to the limit, but the tires are just wide enough that actually the radial flux machine in the end wins. Also because the mechanical structure behind it, to maintain your air gap properly in an axial flux machine, you need much more stiffness than you need in a radial flux machine. Because if you have an impact on the side of the wheel and the wheel moves a little bit like this, then for an axial flux machine it will have a huge influence on the air gap, while for a radial flux machine, if it moves a bit like this, the influence on the air gap is a lot less. So in the end, it's just on the edge, but the radial flux machine was just a bit more efficient. But if you change a couple of parameters on the car, it might be that your optimal solution jumps to the other side again. I think it's the main reason is that people have been looking at in-wheel motors as replacements on current vehicles. So if you take a current car that's still quite heavy, a current EV, especially with the huge batteries that people are putting in nowadays, and and then you combine that with Tesla-like acceleration specifications, then the amount of torque that you need is so ridiculously high. That the in-wheel motor you would need to provide that becomes so unbelievably heavy that you completely lose out on the unsprung weight issue. So if you start from the fact I need a long range, so I need a heavy battery, and from the fact I need sub 5 seconds acceleration, then in-wheel motors won't won't work out. What we did for the Lightyear One, we looked at the optimal configuration of the car as a whole. So if you also have the option to say the car has to be light and we're going to try and still have a lot of range, but do it through efficiency rather than through adding more batteries, then DMO mode can actually be a good solution. So that's the biggest part. You have to look at the whole picture and not just, can I take my regular motor out and put a DMO motor in? Then usually the answer would be no. So for the Lightyear One as a solar car, on the one hand, you want to optimize, of course, the yield that you get from the solar panel. So you want as efficient solar cells you can find as possible. And on the other hand is cost. And if you then plot all the various technologies that are available in terms of yield versus cost, there's a number that does still make sense to get to, and a number that doesn't make sense. How do you set that bar? Well, basically you compare it to other options you have. I can also increase the amount of miles I can drive each year on the sun by making the car more aerodynamic, and there's also a cost associated to that. So by making that comparison, you can basically set a bar for what's the appropriate price for more efficiency in the solar cells. And then you come to, there's this huge gap between about 25% efficient cells that are still based on regular silicon-based technologies, and then you go to the gallium arsenide-based cells, and there's about a factor 10 in price, and you go to, depending when it's one layer or multiple layers, to either 28 or 34%-ish efficiency. So basically optimization will run about halfway through that line. So the optimal choice would be to get the highest efficiency silicon-based solar cells you can. So then you start looking in the market, okay, what's available there. And our partner SunPower has been making IBC silicon cells for years with the highest efficiencies in the market. So that's the ideal choice for a car like the Lightyear One. Actually, the gain is not on cell level. The gain is on module level compared to state-of-the-art panels that are on cars. And the reason for this is not really in the cells themselves, but in the fact that the modules are curved. And the modules have to be curved in order to, one, optimize for the aerodynamics, and second of all, for aesthetics. You can look up the pictures of Stella and all the other solar cars we built that have flat roofs. And what I'm about to explain is exactly the reason why they have flat roofs. But for a consumer car, you have to have a curved roof. When you get a curved roof, then the cells are all facing a different direction towards the sun. And the amount of current that each cell provides is proportional to the amount of sunlight it receives. So if you have a curved roof, no single solar cell will receive the same amount of sunlight. And since they're usually connected in series, because one solar cell gives you about half a volt of voltage and about 6 amps of current in full sun. So it's very low voltage, very high current. So usually you put them in series to get to the same current and a lot higher voltage, because the battery voltage, of course, is about 400 volts. So to facilitate an efficient conversion, you want to put them in series. If you put them in series, then the current has to be equal in all of them. And if then one of them receives less sunlight, it will limit the current through the entire string. So that's what's happening in a curved module. One cell is receiving less sunlight, and that one is limiting all the other ones. And that's where the 20% comes from. If you take a typical car like a Tesla, or we also did the simulation for Fiat Punto, or for the Lightyear One, the number is roughly the same. And you put all the cells in series on the roof, you will lose about 25% of your energy due to this curvature effect. You also get mismatches due to two other reasons between cells. You also have shadows creating mismatches between cells and manufacturing differences. And so what we did in the Lightyear One is, instead of connecting all the cells in series, we made smaller groups of cells and gave each small group its own maximum power point tracker. And that allows us to get this, to not have this effect to such a big extent. So on just this area, the roof might be curved like this, but just on this area, very locally, it's only curved a very little bit. So the mismatches are minimal. So if you give that part one tracker, you still have, you don't lose as much, and you can get this 20% back actually. I think there's a lot still to happen in the coming years. I think in terms of sustainability, we have a long way to go, especially if we look at motors and batteries and the raw materials and where they are coming from. There's a lot to be improved. If we look at motors, my dream is that we get rid of the permanent magnets and go to switch reluctance motors or something like that. And in terms of batteries, of course, personally, at Lightyear, we're not really focused on that right now. So we buy the cells from a tier 1 supplier. But there, I think there's a lot to be gained there as well. And if we look at all the technologies that could improve the efficiency and sustainability of the car, I also see a high potential for better routing algorithms and range prediction. So if you are, we did some studies to see if you can have your car navigation not plan the fastest route or the shortest route, but the most efficient route. You can save quite a lot of energy, actually, on a large simulation for average routes through Europe. And now you cannot pinpoint me on exactly these numbers because I would have to look them up. But I think it's about, you can save about 20% of energy with about 5% time loss. So, and that might be a very interesting trade-off for a consumer to make. If you're not that much in a hurry, you can take the more efficient route. The first one, and I think the biggest one, maybe even the only one, is the exterior shape of the car. You have to be able to fit the solar cells. And that means that the optimization that was already very difficult to get ergonomics and design and aerodynamics aligned in the early stages of the concept of your car has just become more tricky because you now also need to fit the 5 square meters of solar cells. So that's definitely the biggest challenge. Second to that, I think a solar car only makes a lot of sense if the car is very efficient as well. So your next challenge would be to make a very lightweight, aerodynamic, and all of those things in the car itself. So to make it really a solar car, you have to combine the solar generation with the efficiency of the car. And that's when you get the added benefit of a solar car in terms of how many miles you can drive each year on the sun. Because of course that's basically just the ratio between how much you generate and how much you consume. And for me, it's only a solar car if that number is significant. So if it's more than 50% of what you typically do over an entire year, I think that's the point where you can call it a solar car. First of all, trying to take all those use cases into account and then looking at, okay, what's the environmental temperature, what's the inside temperature, and how do I what's the most efficient way to get heat to the right place. There will be a significant impact on your range in colder climates, simply because you do need to heat the battery and you will need to heat the cabin, and that does take energy, even though we have the heat pump in, so that will help a lot, but still it's... and also, the unfortunate thing is the amount of heat you need to heat a cabin doesn't really change if you make a more efficient car, but the amount of power you consume on other stuff, it lowers drastically. So relatively, the impact is still quite significant in the car because the rest of the car is so efficient, and this impact, you cannot really change that much.